The first place team got like a really nice softball jacket. The second place team got a bag. So you guys got that? Yeah. Well, I didn't, but they did. But then like the third place team got
Yes, we do.
halters, I think.
Yeah.
And then third place got It's not the other day. We have so much. Oh my God, how are you? So cute.
All right, let's see here. So, things coming up. We got mastering tonight and Wednesday night. Your final few masterings. Then we're going to do an individual quiz today covering thermodynamics because we haven't really had a quiz over the rest of thermodynamics. Student symposium is tomorrow. For you to get credit for going, you attend an entire session, summarize all the talks in the session, and email that to me. And then our third exam is April 23rd, unless you want to take it early, because that is the last week of class. If you want to take it early, come see me after class so I can get a list of how many people want to take it early. And we can organize a time for that. Any questions about any of that? All right, so now that we can do a fairly good net ionic equation, predict the products, figure out who's oxidized and who's reduced in a solution, we want to put it all together in what's called a voltaic cell. So, a voltaic cell right, there's two types of cells. There's voltaic and galvanic. The voltaic cell is the one that produces electricity. It has an output of energy. So when we think about voltaic cells and this output of energy, let me get a better sheet. What measurement do we use to measure electricity? Volts, right? We're going to talk about volts, which makes sense because we're doing a voltaic cell, which means the electricity is coming out. We're going to measure it in volts. So hopefully that reminds you which one's which. The voltaic cell makes volts, which means it's producing electricity. That voltage produced is a measure of spontaneity. So, since I can measure spontaneity, which is a measurement of, I'll take either one, two letters. Delta G or, yes, right? All those. Lucky for you, we can combine all those things. So if I know spontaneity, I know equilibrium, I know delta G, which means that I know H and S and Q and K. We'll combine them all together. So the cell voltage depends on the half reactions taking place. And the concentrations of all the species in solution. Why do I care about concentration? Which letter, two options, which two letters depend on concentration? K and the other one that's like K but not K. Q, right? So the concentrations tell you about K or Q, and then those combine with this to tell me if it's spontaneous or not. So we call that E superscript 0 cell. So what is that 0 or that O or whatever? What does that tell me about what state I'm in? Standard state. So we're going to call that a standard state cell. And so if I know the voltage, voltage. If I know the voltage, I'm at standard state, then I can figure out things about K and Q and G and all those kinds of things. So it tells us information about the cell. All right, so let's go ahead and build a cell that has this reaction in it. I have copper and silver, making copper 2+ and silver solid. So right, in a voltaic cell, the electrons are being pushed they're going to be pushed through an external circuit. And the electrons are going to flow from high electron concentration to low electron concentration. All right, so here we have this guy right here. We'll look at the two half reactions, figure out which one will be the higher electron concentration, which one will be the lower, and then we'll build a cell around it. All right, so let's take the copper half first. All right, is this the oxidation or reduction half reaction? Oxidation. How do you know it's the oxidation? It loses electrons. In other words, it has them as a product. The oxidation has increased. It's gone from 0 to +2. So how many electrons do I need as a product? 2. So let me write this all down. This is the oxidation. What's the oxidation half reaction? I've produced 2 electrons. All right, we'll take a look at the silver. Okay, what's happening to my silver oxidation state? Increasing or decreasing? It is decreasing, so what does that tell you about the reaction? The reduction. So do I have electrons as a reactant or a product? Okay, and how many do I need? 2. All right, right, are we now mass and charge balance? Is everybody happy with this? Okay. Of my oxidation reaction or the reduction reaction, which one is going to have a high electron concentration in the beaker? This one produces electrons, right? So as it goes forward, as I keep oxidizing copper, I'm going to keep making electrons, right? You make them, you make them. So this is our high electron concentration reaction. And then we're going to use them on the other side. So hopefully everyone's ready for a little amazing drawing I'm about to do. Let me draw it first and then you'll draw yours because it's kind of takes a lot of space. All right, so here we have, you're going to draw 2 beakers. Okay, you got your 2 beakers. And in this one, I have my piece of copper solid. I got my silver solid in the other beaker. There's my external circuit. So what must be in the solution if this is the copper solid over here? What also must be in here?
Silver.
Well, we're actually going to put the silvers over here. We're going to put the coppers over here, right? Because copper is making more of this. That's where it's kind of tricky. I'm going to put my copper, everything copper in one beaker, and everything silver in the other beaker. So this is now my oxidation half reaction beaker. All right, so I got everything oxidized over on one side, everything reduced all on the other side. Looking at this, my oxidation half reaction, in this beaker, am I making more copper ions or am I using the copper ions up? Making more, right? So it must mean they're coming off the metal into solution. Right, that's what my half reaction told me. What about these silver ions? Am I making more ions or using them up? Using them up, so they are becoming the metal. All right, if this is my high electron concentration, this is my low one, the electrons are going to travel from here to here through there. So electrons are being produced, right? I'm making copper 2+ and some electrons. The electrons are leaving the beaker, going through my voltmeter, coming over here where they can be used up. The last part of my amazing sketch, which hopefully everyone's looks as awesome as this one. What is the issue in this one beaker? What's happening to my charge? I'm making lots and lots and lots of copper +2. It's increasing, right? I have lots and lots of charge buildup over here. What's happening to my charge over here? Decreasing. The problem is you can't make a lot of charge without balancing it out, right? When we always talk about our equations, we're talking about charge balance and mass balance. So right now my beaker is totally mass balanced. It's not charge balanced. You can't have a beaker of just all +2 things. So what we do is make something amazing. It looks like this. Make a salt bridge. This is actually what's happening in all your tiny little batteries that are liquid based, not solid state batteries. Those are different. So like all your regular like batteries in your remote controls. Except it's not 2 beakers, obviously. They're all squished together. But we're going to build a salt bridge to balance out the charges. All right, so if I'm making lots and lots of copper plus 2 in the beaker, what kind of charge do I need to balance it out? More positive things or more negative things? I need more negative things, so how about I put in some Cl minus? That sounds great. We'll put some Cl minuses in here. I just picked a random salt. It could have been anything. It could have been, my notes have nitrate. You could use nitrate, chlorine, bromine, iodine. Whatever, something with a -1, -2 even, sulfate. All right, so what's going on over here in terms of charge? What do I need to balance this guy out? I need some more positive stuff. What? Sodium, that sounds great. That sounds salty. All right, so in my original salt bridge, I had sodium chlorides. The sodiums are going to head this way to balance it out, and the chlorines are going to head this way to balance it out. All right, so there's a fancy name for the oxidation half reaction end of the reaction. That's the anode. The anode is the oxidation side of it, and it's where the electrons are produced. It's the high electron concentration. Anyone know what the other one's called? Cathode. So the cathode is where the electrons end up, and they pull the electrons into solution.
So that would be like low electron?
It's a low electron concentration initially, right? Eventually it all evens out, at which point your battery's dead. But, all right, so here are my helpful mnemonics to try and remember where everything goes. All right, the anode is the oxidation. Those are both your vowels. Your cathode is your reduction. Those are both your consonants. Over here, we're going to have an increase in oxidation state. Another vowel. Over here, we have our reduction in oxidation state. And electrons always flow A to B to C. They always flow anode through the bridge to the cathode. So every time you sketch these, electrons always start off the anode, they go through a bridge, they end up at the cathode. So A to B to C. And A is your other vowel, so it has to be the oxidation. Look how easy that is. Makes sense. Oh, yeah, which way? There we go. All right, so it's awesome. Oh, question first. Question. A to B to C.
Like what?
The electrons all get made over here in the anode.
Oh, okay.
Then they flow through a bridge of some sort, and they all end up in the cathode.
Oh, not the salt bridge.
Yeah, sorry, the top voltmeter bridge. All right, so awesome as it would be. Oh, question first, Nathan.
I was just going to say, in AP we had a kind of a silly mnemonic that helped remember this. That was an ox chased a red cat.
Oh,
So
that's good too. Oxidation, then this way, then the reduction. That's good too. So lots of different funny phrases we can make. You can do the Leo goes grr, ox and red cats, all good stuff. Okay. So that was kind of intensive to draw that, right? There is a shorthand way that we're going to use to tell the same information, but not do an entire drawing. The shorthand we're going to use looks like this. So for the exact same cell, that tells me all the same information as that beautiful diagram that I just made, but much easier. All right, so what this is telling me So that's the stuff going on at the anode. This little double line tells me that's the bridge. That's the, everything to one side of the double line is anode. Everything to the right is the cathode. Which means that this side is my oxidation. This side's my reduction. And the single line tells me that there's a phase separation, that there is a difference between this copper and the copper plus 2. Because, right, I didn't tell you what states of matter they are, but by having a line in between them, it's telling you this one must be a different phase than this one. Since it's plus 2, it's probably aqueous, so this is solid. Okay, let's practice doing some more cells. Oh yeah, oh, Mallory question? No, just stretch, big stretch. No, it's good. All right, let's say I have this. Okay, so draw the following reactions in shorthand voltaic cell notation, just like we did. Anode, double line, cathode. So I have chromium and iron plus 2 to make a chromium ion and iron solid. All right, looking at that, what is the metal that's being oxidized? Okay, so does that go on the left or the right of my cell if it's being oxidized? Right, so our cell goes A, B, C. And if chromium's being oxidized, does it go on the A side or the C side? A side.
Do we include coefficients?
Not in the shorthand. No. And by convention, we always put the metals on the farthest outside, and everything is not a metal on the inside. Like a solid metal. So it looks something like that. Okay, what if I have zinc solid and iron plus 2 going to zinc plus 2 and iron solid. Which metal goes in the anode? Okay, so zinc is going from 0 to plus 2 and iron is going 2 plus down to 0. So which one's the oxidation? Zinc or the iron? Okay, put that on the outside. And then since there's only one option, Okay, what if I have what if you have a half reaction that doesn't make a solid? I have this. Let's say I have cobalt and zinc making zinc plus 2 and cobalt plus 2. First question, who is being oxidized, the zinc or the cobalt? Zinc, okay. So what side does that go on, the anode or the cathode? Okay. So that part is like we've done before. All right, what does this single line tell me? Separation of state, right? Looking at those two cobalts, are they different states or the same state? So do I get to put a line in between them? No, there's no line because they're the same, they're both aqueous. We just put a comma.
How would that look in an actual cell?
There is a piece of metal. It's usually a piece of platinum. So that's the last. If there's no metal being made on one side or the other, you have to have one experimentally because you can't force an ion into another ion without a surface for it to occur on, which, fascinating. I'd love to tell you more about surface chemistry. But for now, you can just say the two ions have to have some platinum. All right, how do we feel about shorthand? Fairly confident? Yeah.
Can you show an example when it has other things, or was that that we do, like, what if there was another metal in that equation? Does that?
No, ask it again.
Okay, so what if there was like the cobalt and zinc and iron? I don't know if that can happen, but how would you set that up?
It could happen, but not in this class.
Okay.
In this class, there's always going to be one thing oxidized, one thing reduced. That's it. We could do a 3 triangle kind of thing, but we'll save that. We'll save that for like juniors and seniors. We'll work up to that. Or a chemistry class, 90% of you will never take. But if you want to come by, we can talk about it. We can talk about oxidation reduction in the molten state. That's pretty neat. Or oxidation reductions at mercury drops. We can do a little electron. Or we can make gold fiber microelectrodes and modify them and then do electron. Just the best. Just the best. Can't believe there aren't more electrochemists out there. Just the neatest thing. All right. So now we can draw a cell, which means we can predict what products and reactants will be made. But the whole point of having a voltaic cell, right, is to make some voltage. So we want to be able to say, these are the things going in. We want to be able to measure that cell voltage. So, just like I had before, cell voltage. So cell voltage is going to depend on which two half reactions to put together and what concentrations you have of everybody. Right, so our standard cell voltage is measured at concentrations of 1 molar, gases at 1 atmosphere, Everybody at 25 degrees Celsius, right? Standard, like we've done standard for everything else. If I am at my standard states, where most likely am I in terms of what K equals? It should be equilibrium, right? K should be 1 if everything's 1, just like we did last chapter. If everything's 1, K is probably 1. I'm at equilibrium. If I'm at equilibrium, how much electron transport's probably going on? Very little, because both the cells are maxed out. They've done everything they're going to do, for the most part. So what's current a measure of? Anyone know from their physics classes? The electron flow, right? So current is the flow of electrons where its unit is volts. Amps, really. Current's amps, but we're going to talk about volts. Anyway, another great conversation about resistance, circuits, building a circuit with a little breadboard. You put the little, like, everyone else have a breadboard when they were growing? A little fake breadboard where you could like put it all together and like you can make doorbells ring. And what did you guys do for Christmas gifts? I got my build my own physics set. That was pretty neat. I got my own chemistry set. No? It was I got Where in the World's Carmen Sandiego one year. That was a pretty exciting game. That was the best game, right? My brother and I was in charge of looking at the facts in the World Almanac. My brother was in charge of pressing the keys on the computer. So we had a division of labor. Because I'm a fat checker before the age of Google, where you had to have the World Almanac, you had to flip through and find the right map, and that tells you how old I am, just saying. All right. We did have a pretty cool Apple IIe when I was growing up. Pretty big deal. Which nobody knows. All right, so here we have our standard cell voltage. Let's say, for example, I have this reaction. All right, so I've made iron solid and some protons at 1 molar make some iron plus 2 at 1 molar and some pure hydrogen gas. Does everything appear to be a standard state? Good, it should, because that's my point. Should be a standard state. Good, everybody's at 1, 1, 1, 1. I would figure... We'll talk about here in a second how to figure this out. But the E0 for this reaction is positive 0.44 volts. A positive E0 is going to tell us that this reaction goes forward as written. It is spontaneous in the format it is written. And obviously the opposite point would be true. A negative E0 would be non-spontaneous. All right, so the follow-up question is going to be, how do we determine what the E0 is of a reaction? Apparently I forgot to write the rest of the sentence. Each with its own cliffhanger. All right, so any redox reaction, right, can be split into 2 half reactions, just as we've done a million times. Each with its own standard state cell potential. Therefore, its own, what did I want to say? Oh. Just go ahead and stop the sentence there. This makes more sense. Each with its own standard state cell potential. So we determine we're going to determine the overall E cell from the two half reactions, right? The electrons are flowing anode to cathode. So if I'm flowing anode to cathode, where do the electrons eventually end up? Right, so that'll be E final. Right, if I was doing any other kind of standard state thing, I'd do final minus initial. But the electrons end up at the cathode. Starting off from the anode. So it's more appropriate to write it this way. The E0 the cathode minus E0 the anode. So, for example, let's say I had this reaction. Right, here's my little reaction. And I want to figure out what the overall E cell is for this reaction. You will need to use the table that's in your book to find out the standard state cell potentials. So, I gave you one in your PowerPoints, but it's the same one that's in your textbook because it's really tiny to see on here. Now, the key to this table, most common mistake that people make, is not, I guess there's two mistakes. One, you end up using the wrong half reaction. And two, you change the sign or do something crazy with it. So, in this case, let's see if I can zoom in and find it. Okay, here's zinc, right? You can't even see that. There we are. Zinc plus 2 electrons make a zinc solid. Is that the way it is written in your half reaction that I just gave you? How is this written, as an oxidation or reduction? It's written as a reduction. How are we using it in my cell? As an oxidation. Doesn't matter. We're going to plug it in just as is.
You don't reverse the sign, right?
No, common mistake is to reverse the sign. Do not reverse the sign and do not multiply by stoichiometric coefficients. So, while it's similar to what we've done with thermodynamics, completely different rules. Because we're doing a subtraction, it's going to take care of the sign change. So if you sign change and subtract, you've done the same thing twice. So just leave the sign as is, but plug it into the right part, right? So I just said this is the anode, so the value for that all right, so then you got to figure out what the cathode half reaction is. And it happens to be that this is a very special reaction that has 0 as a standard state reaction. It's actually hydrogen is what we measure everything else against. So you take the value off the table for this reaction, make sure you just plug it into the right part of the equation. Don't change the sign, don't multiply it by a stoichiometric coefficient, you just leave it. If it's a positive value, what does that tell you about the spontaneity of the reaction? Spontaneous. All right, I'm going to save the rest of that for Wednesday, so we have time for our quiz. Yay!